Hi, my name is Connor Bush, and today I will be explaining a little bit about the van der Waals equation of state, its relevance, and a little bit about its parameters. So here we have van der Waals equation. Basically, it's a modification of the ideal gas law, where it takes into consideration that a gas does not exist as just a particle. It has mass and exists and takes up space. So we have two additional parameters. We have an A right here, and then we also have this B. And like I said, that accounts for the particles taking up space. Right here, this is what a plot looks like of pressure versus volume for different temperatures, and we're sort of interested in the critical temperature because of this inflection point, and because of that we know that the first and second derivatives equal 0, so that will help us find what our A and B parameters are. So we can start by taking the derivative of this equation with respect to volume. Okay. 1 second. Okay, I got my pen to work. So the derivative of this equation with respect to volume, and notice that we have a subscript of T or C right here that relates the critical temperature, critical volume, and critical pressure. So the derivative here goes like this. And then the second derivative will be this. And let me put in that. Oops. So with this, like I was saying about the inflection point, we can set these equal to 0 to help us further get to isolate the A and B. So I can just say that the gas constant times the critical temperature over the critical volume minus B squared equals 2A over the critical volume cubed. And same thing with the second derivative equation. So now that we have this, we can multiply by the reciprocal of the respective fractions. So over here, we're going to multiply this by the reciprocal of this fraction. So that will look something like this. So we already see some cancellations here. And then same with the other side, so we're going to multiply this by the reciprocal of this. So we have 2A times BC to the fourth over 6A times the critical volume cubed. So notice we have our A parameter cancel out. So we have this. I'll simplify it a little more so it's not too messy. So we have B squared. Actually, this should be cubed, or this should be squared rather, and this should be to the first. So we just have this over 2 equals VC over 3. So if we just cross multiply, we have this. And then if we isolate B, we get B equals V, the critical volume, over 3. So this is our first parameter of the two. So if we plug this back into this equation here, we can solve for A. So so we can just do some algebra to get A by itself. So it will look something like this. And then cross multiply after you get rid of the fraction in the denominator. So it will be 9R times the critical temperature over 4 VC equals 2A over VC cubed. And then we can cross multiply. So this should be squared. And then to get A by itself, we do 9RTC VC over 8. And that's our A parameter. So with this, we can put it back into this equation, our original one here, so that we can model what any real gas would be regardless of its identity, and that will also help us find the compressibility factor, which we will talk about in a little bit once we find it. So it goes like this. So we have a gas constant times the critical temperature over critical volume minus B, which is critical volume over 3. This is subtracted by A, which is 9R times critical temperature times critical volume over 8, all over critical volume squared. Copied correctly. So now what we can do, we can solve, what we're going to try to do is find the compressibility factor, Z, and that equals Z equals PC VC over RT. So let's try to get it into this form here. So then we can move the fraction in the denominator and move it so that we don't have that. So we have 3 times gas constant times critical temperature over 2 times our critical volume, and that's subtracted by 9R times critical temperature over 8 times the critical volume. If we multiply this left fraction by 4 over 4, we can finally get that this subtracts to get 3 times the gas constant times our critical temperature over 8 times our critical volume, and remember this equals our critical pressure. So if we get it in terms of Z here, we get that PC over times VC over RTC equals 3/8, and this equals Z. So this compressibility factor talks about the deviation from an ideal gas. So the compressibility factor for an ideal gas is just 1. So if we put this and get it equal to our critical volume, we can put the A and B back in, so we can have what A and B would be for any real gas that relates to what you're looking for. So remember that we'll start with B because that's a little less complex. So B equals, actually I'm ahead of myself, we need to get this in terms of our volume. So our critical volume equals 3 times R times the critical temperature over 8 times our critical pressure. So this, we're going to do B equals, and it's our critical volume over 3, so 3 times R times our critical temperature over 8 times our critical pressure over 3. And then this equals, these 3's cancel out, so we're left with R times our critical temperature equals 8 times our critical pressure. So that's our B parameter for any real gas. And then our A, which is a little more complex, we'll put it up. We'll put it right here. A equals 9 times R times our critical temperature times 3R TC over 8 PC all over 8. So then, if we do some more algebra here, we get 27 R squared times our critical temperature squared over 64 times our critical pressure. And this equals A. So, essentially here, the van der Waals equation of state is for non-ideal gases or real gases that take into account that there's mass and it takes up space. And with the compressibility factor, Z, we can find the deviation from the behavior of an ideal gas. And with this A and B parameter solved in terms of the critical temperature and critical pressure, we can model that in for any real gas. So, thank you.